Okay. Hi and good morning, everyone. I'm Mariam Fazal. I'm a professor in electrical and computer engineering. And today it's my great pleasure to introduce Professor Tara Javidi from UC San Diego, and actually to welcome her back to UW, well, at least for a virtual visit. Tara received her bachelor's in electrical engineering from Sharif University in Iran, and she has 2 master's degrees from University of Michigan, one in electrical engineering, one in applied math, as well as her PhD from University of Michigan in electrical and computer science. From 2002 to 2004, she was actually an assistant professor in our own department. We're very happy to have her here for a bit at UW. In 2005, she joined University of California in San Diego, where she is currently a professor of electrical and computer engineering. And she's the co-director of Center for Machine Integrated Computing and Security. Tara's research interests are in the theory of active learning, statistical inference, information theory, very broad set of interests, also including stochastic control and communication networks. So with that, I'll welcome back Tara to UW ECE, and looking forward to your talk.
Thank you so much, Mariam. Thank you for inviting me. As I was telling you, I was really hoping for a nice revisit to campus and get to see everybody, all my old friends who are now very important people running the campus, as I learned. Oh well, I'll come back. So thank you for hosting me, and I'm very happy to be giving this talk. So today I'm going to talk about black box optimization, this is most of the talk is going to be on some theoretical results that my really brilliant student Shekhar Shubhanshu has obtained. And then at the end of the talk, I will also talk about applying some of these theory, at least in theory, and then sort of coming up with heuristics with joint work. Actually, oh, I'm sorry, I'm missing the name of my collaborator, Farinas Kushan, who is on the computer engineering side, has introduced the application to compression of deep neural networks and acceleration, and that work is joint work with Mohammad Samraq and Mojan Jawaharpay. At the end of the talk, I'll show you some more practical implementations. So let's get started. So let me just describe what I call black box optimization. So consider a simple function f on some domain x that gives you a functional that gives you a value in R, and we would like to optimize this function with the caveat that f is not known explicitly to us. So I don't have a closed form formula for f so that I can optimize it. And in fact, I might actually lack quite a lot of knowledge about the structures of this problem and this function. So the way I would like to optimize it, the only way that's left for me to optimize it is to access it through evaluations that are expensive. So I can submit x and get a noisy version of f of x, and I would like to sort of repeat this process in order to find the optimizer. So the problem of black box optimization, or some people call it zeroth order optimization, is to design a sequential strategy of selecting n query points x1 to xn in this curly x to efficiently optimize f over a horizon n over these samples or some queries n. And the performance metric that people look at are two different types. They're closely related, but you'll see the sort of distinction between them. The first one is called simple regret. So these are the difference will be between what you will find at the end of the process of exploring this function f. So you will submit x of n as the best optimizer, and you will compare the performance of a oracle that would know the function f and would have optimized it and find x star, the optimizer. You compare yourself to the performance of that oracle. So that's called simple regret, because basically all the process in the middle, x1 to xn minus 1, are just exploration. You can do anything you like. Another maybe more complicated notion of performance is cumulative regret, where you're actually penalized every point in time up to the horizon n relative to this oracle response f of x star. In this talk, for simplicity, let's assume x is some cube in RD. So just a compact subset of RD will do, even though the results can often be generalized to more complicated spaces of x. The problem that I would argue, it comes up in engineering all the time. So in my former life, in fact, when I started at UW, I was focusing on wireless networking. So what I'm showing you, in fact, I don't know if it's visible on the screen, is the layout of a wireless network that we have set up in my building, consisting of a few nodes, some of them programmable and some of them are just sniffing the wireless medium. And the job of my job in back then was to actually optimize these programmable clients in terms of the setting of these wireless devices. So you can imagine the setting of every box to be put together into a long vector of x. Often these networks are so complicated that we don't have any closed form understanding of how these settings will affect. And network designers often are left with heuristically searching in the space of the settings and play with this, run the network for a while, measure the performance, let's say in terms of error probability or power consumption or whatnot, whatever measure of performance that you care, and come back as how good this setting is. And then you just do this for a while, right? So that's exactly the setup that I just posed. And of course, it's a noisy version because you're not going to be able to run these networks for very long, right? So that like whatever you're measuring, it's averaged out over a small window of time relative to the time that the network will be deployed. Another example, and the example that these days is very popular and has brought a lot of attention to this black box optimization, is the problem of acceleration of a deep neural network on a mobile device. I'm going to talk about this a little bit in more details. So the idea is that you have a neural net. Often these are incredibly expensive to run on smaller devices. So you usually have a data scientist and an engineer working together to decide what parts of this neural net they can sort of throw away, which hyperparameters they can sort of optimize over in order to get a good performance in terms of hardware cost and accuracy from this network. So, and actually, in fact, these two applications give a good sense of what this simple regret versus cumulative regret is. So let me just talk about this. So I just described this. So in the network optimization, I have the set of possible settings. My network performance is the unknown function f, and the horizon of empirically tuning the network is this n. So if you have time to train the network, you can do a simple regret. If you're using the network as you go, of course, you don't want to take crazy settings that you already know are not so good, right? So you want to minimize the interruption to the network operation. So you would think about cumulative regret. So now, of course, this problem in general is very ill-posed, right? Because unless I tell you some things and give you some prior assumption on f of x, it really makes no, there's nothing you can do except for search the whole space for the maximizer. So in most of the literature, you have to have some assumptions about how f of x and how f of x prime are related to each other as a function of proximity between x and x prime, right? So that will help you, hopefully, by testing f of x to give you some information about some x primes and having some prediction as what the value of the function will be. And the first type of assumptions that I like to talk about in this talk is when we assume that f is an unknown function, yet it's a sample drawn from a known Gaussian process, a zero mean Gaussian process with a given covariance function. So I don't know the function itself, but I assume that it's pulled out of a Gaussian process with zero mean and a given covariance matrix. And the observation model is also Gaussian. So I'm observing y's as a function of f of x plus a noise that I, again, know the variance of this noise process. So in this setup, the problem becomes far simpler. Why? Because I have a Gaussian setting. So I start with a Gaussian prior, and now I can compute for every sample x that I have collected, or maybe x1 to xt that I have looked, xt minus 1 that I have looked at. I can describe the process still remains Gaussian. It's a linear observation. So the process remains to be Gaussian, and all I have to keep track of is the posterior mean and posterior variances at all points. And this can be computed as a linear estimator that we have seen in your basic signal processing classes. So you can compute the covariance matrices between the observations, and that basically gives you the best estimator of the posterior mean and the variance. Okay. So in this
quick question.
Sure.
Sorry. So f is a Gaussian function, and eta is also Gaussian noise.
Eta is Gaussian noise. F is a sample drawn from a Gaussian process. So let's think about X being a discrete set. So let's say X has it's like one dimension, and I look at X1, X2, and so all it says is that the process f of X is a Gaussian process as a function of X1, X2, Xn, right? So let's say, right, like, so X1, let's say, is 1, 2, 3, I rank order them. So that is a Gaussian process.
I see.
Right? So if it's a Gaussian process, it's described with its second moments. Mm-hmm. So every time I have to get a guess, I can calculate the remaining process will remain Gaussian, and the mean and the posterior mean and posterior variance can be computed.
So the sampling is Gaussian.
Yeah, so you imagine at the beginning you sampled from a Gaussian prior, and now the function is fixed and forced to you. The noise is Gaussian, so now you're making a Gaussian observation of a Gaussian vector.
I see.
Right,
okay,
right.
Yeah.
So you have a Gaussian vector that you're basically estimating.
Yeah, thank you.
Yeah, sure. Okay, so this figure on the right shows, actually, I should have actually seen, answering your question, Mariam, I should have shown this. So this is showing my process was a sampled process. The black function is the process itself. I have sampled it at the red spots, and I have observed the f of x1, x2, and so on. And now, given those values, I have shrunk my posterior mean and variance, which was around 0. It was a 0 mean prior with a known variance. Now I have shrunk it and made it sort of tighter around the real sample, the sample that was drawn. So this actually is used a lot in this second class of problems I was telling you is very popular. It's called hyperparameter tuning in machine learning. So the idea, as I said, is that you have these models and you would like to map them on different hardware. So there are a lot of hyperparameters or maybe compression techniques that you can use on these neural nets. And normally people imagine a data scientist and an engineer working together to decide what the right hyperparameters are. And this function optimization framework is really replacing that iterative process between the engineer and the data scientist with a sort of an engine of optimization engine, basically. And in this setup, really the hyperparameters of the neural nets create a classifier, define the classifier, the best trained classifier, and the performance on the test set is usually the function that you're trying to optimize, and you're going to try this over time. If you are, again, if you're only interested in training your network and then you can take crazy exploration decisions, you can use some hyperparameters that are off just to learn something. If you're actually using the model as you go, you would like to do a minimum cumulative regret. Right. So these are this is very popular, and the Bayesian version of this is often used, where people assume for these problems that a very popular covariance function that is assumed is known as a Matern family, and basically I'm writing down the covariance function as describing the correlation between the value of the function at point x and x prime. And as you can see, it's a bit of an exponential component here. I don't know if you see my the exponent as a function of the distance between the two value, and there's a polynomial term. The popular family of Matern kernels that are used in practice are parameterized by this factor nu, and this nu, you know, I'm going to talk about, you know, these are the target family that we're really interested to perform well, right? As you can see, so as 2 points sort of go away from each other, their dependence sort of decreases, right? That's roughly the intuition between these. Okay. So, so I'm going to take a bit of a time to explain what the setup in the prior work is, and where we sort of started looking at this problem slightly in a different framework. And I should say, I should give credit to Galen Reeves. I was giving a talk on active hypothesis testing, and he introduced me to this problem and said, can you actually hypothesize the maximizer's location and then design, you know, use your active hypothesis testing for solving this problem? Again, remember, I'm going back and forth between measuring something or submitting a query and then looking at noisy version, which is very similar to active hypothesis testing. So let me try to understand the prior, to explain the prior work. And there are people at UW who are very, very, have done excellent work in the space. So I apologize if to those of you who are familiar with the state of the art. So often, as I said, people look at the posterior behavior, the posterior mean and the variance, and they query the next variable, the next sample to be queried, x of t, to be maximizing something that is called an acquisition function. So they have a sense of how informative sample x would be, and then they try to maximize that informativity. And this alpha of x, this acquisition function, is the utility of querying x, and often it balances exploration and exploitation. And the common ones, the most popular ones, is you try to estimate what is the probability that this value is going to improve on the values you have seen. So what is the probability, you know, that this function is larger than some tau? It could be an expected improvement. What is, you know, what you will look at the value of the function and say, what is the probability? What is the expected improvements in the value that I will actually obtain? A simpler notion is an upper confidence bound. You can look at the posterior mean and look at the linear combination of the posterior mean and the posterior variance. And that will give you the figure that I showed you, that will give you an upper bound as well as a lower bound, but the upper bound is often, you know, can be viewed as an acquisition function. So, and so these are the common ones. There are other ones, but this is good to get an intuition. And of course, where we came at this problem, we were surprised because alpha of x itself is often non-convex with a lot of local maxima. So even optimizing, and it was not clear how even to choose x to optimize alpha of x. So that was the first problem that becomes critical. So what people practically do is practically discretize x and look at, do a, you know, sort of a exhaustive search over that discretization, which immediately meant that this complexity of these algorithms are going to be very poor with dimensions, because if I discretize, the dimensions will show up in terms of an exponential complexity of the search over to optimize alpha. So that was the first thing that we thought, can we do better? Can we actually come up with algorithms that don't explode with dimensions? The second aspect of the prior work that I would like to talk about is the kind of regress analysis that you would get from these. So existing bounds on cumulative regret, and you can get similar bounds in terms of simple regret, are the following form, that they will always show that the regret is bounded by a function of n, the number of samples, and a function of what is known as gamma of n, or the maximum information gain. So this is, you can define this gamma of n as the supremum over the choice of samples that knowing y at those points gives the mutual information that you can get that gives information about the function itself. So you can calculate this mutual information, and this ends up being sort of the upper bound on on the regret that you can control. And for specific kernels like matern kernels, you can often go and calculate this quantity and hence get specific bounds for what the regret looks like for these families. And to just the second point that we were feeling like this is actually an overkill is that gamma of n gives you a maximum information about function f. And if you think about it from the perspective of hypothesizing the position of the maximizer, you should really be looking for maximum mutual information about the position of x star and not necessarily f. F could be really complex, but position of x star might be cheap. So that's the second thing that we wanted to actually address. And we were hoping that this way of looking at hypothesis testing will solve the problem. Let me show you an example to crystallize this. So this is a Gaussian process, which looks very complicated. It's a fractal structure. So you can actually compute gamma of n for this. So this is actually, Shekhar has gotten very good at building this pathological example. The gamma of n is very large, actually it grows with n, it's a linear function, but the maximizer is very, very simple. It's either this point or the flipped version often. So in other words, with one sample, I could have found the maximizer, but it takes me a long time to learn the full function because of its fractal structure. So we could come up with an example when we knew these regret bounds are too pessimistic and we were looking for algorithms that can do better in terms of using the geometry. So I'm going to give the overview of what we did, which is different, and then I will go into describing the algorithm and so on. So let me just give you the overview. So the first thing that we did, the first contribution that I would say Shekhar has is the algorithmic improvement. So if you remember, when we were to solve the optimization problem, all prior work, except for one, which I will come back at the end and compare our results for the two, there was a discretization of the sample space X, which meant that you have a exponential growth in terms of dimensions and the complexity of the algorithm. And you always had to do this auxiliary optimization of acquisition function over this discretized space. So algorithmically, and I will show you the algorithm, what we did, we said we don't need to discretize the space offline. We can discretize the space in an adaptive fashion. And that will give us an improvement in terms of complexity. So I will show you that the complexity of our algorithm, computation complexity of our algorithm grows only linearly with dimensions. But also, it allows this adaptive structure to adaptively and opportunistically adapt to the simpler structure of function f if such a simpler structure exists. So you don't assume it, but as you go on, if the structure is simpler, our algorithm will zoom in faster on the lower dimensional maybe embedding that might exist in your function. And again, I will show you some example with that. The second set of contributions is in terms of analysis. So the regret analysis that we have on these problems uses the geometry, and hence instead of being informational type, using this gamma of n, this information about the function, it really is a dimensional type bound. It basically gives you a sense of the structure, the underlying structure of the function. And so I will show you the regret bounds, and what I can say in summary is that it's better than the regret bounds in prior work. It's sometimes strictly better, in particular for matern kernels of relatively general dimensions. The results are strictly tighter, and in particular, it gives us the first sublinear bounds for exponential kernels. These are matern kernels when the nu is the smallest, is a half. So let me tell you what the algorithm does, and kind of shed light on why I was saying this is this view of active hypothesis test is useful. So the construction of an algorithm is to take the function and replace it with piecewise constant upper bound confidence intervals. So we were just going to get a really simple approximation of the original function with piecewise constant upper bound. Okay, so this is my function. I have evaluated at these points and observed these values. So I'm going to use what I know about the uncertainties or the noise, and as well as the Gaussian structure, to get these upper bound functions. The upper bound relies on two bounds. One bound is simple. It's basically mu, the posterior mu t, plus the linear plus some sort of a constant weighted variance. So this quantity is what is called upper confidence bound that is used in the literature. So our bound includes this, but it has a second component, which is this quantity, and it's really a function as an upper bound on how much variation this function will do in the cell that the function is constant over. So I have used these piecewise constant functions. The width of the constant piece is going to be determined by how much variation a Gaussian process can do. And this is a geometric phenomenon that Shekhar could show, that if you pull a Gaussian process, a sample from a Gaussian process with a given kernel, you can actually bound how much variation you have in any subset, or in fact, you can show it's a Lipschitz function, and you can get guarantees for what that Lipschitz constant is. So that's how he finds this second quantity. And now you have this piecewise function with upper bounds. You look at these and you maximally pick the set that gives you the maximum, and you decide, okay, this is the right place to further explore. And you do this by either sampling again, in which case that if, basically you're smoothing the noise. If you sample in the same location, the middle of this cell, you will just reduce the noise. Or if you decide the noise is small, the problem is the variation is too large because the size of the cell is large, then you actually take that subset and break it in two pieces. That's the adaptive discretization. So instead of looking at one point in the middle, now I look at 2 points that are maximally breaking this region. And you do this algorithm, you sort of do this over and over. So to just formalize what I just described, and you can do this again. Now, if you look back, now the maximizer is another subset, and I can do the same thing, either sample again, or if this uncertainty is due to the variations because the set is really large, what you do is you break it. So you just actually build this sort of this adaptive discretization of the space. So this is the formalized way. So basically we define a fixed tree of partition of the space where, you can sort of think about this decision tree of middle points, 1/4 points, and so on and so forth. And you create these cells, and the cells are such that they're sort of size are getting smaller as you go lower and lower in the decision tree. You can easily build it by halving, picking half points if you, for example, look at a d-dimensional cube. So in round T, you maintain a sort of a set of leaf nodes, and each leaf node represents a cell. A cell has a center as well as a width and a variations. So you keep track of these quantities and you build these upper bounds for your function. Refine, you make a decision to refine, as I said, if the variance is small compared to variations in the cell, or you evaluate by saying, okay, I have a noise in observation, so let me reevaluate that and average that. So this is the sort of the structure, the formal structure of the algorithm as I was just showing. The complexity you can show that grows only linearly with dimension, because when I break my cell, I only have to break it along the longest side of it. So you're basically breaking one dimension at a time. So it grows linearly. And then under assumptions, mild technical conditions on the kernel, and this would be, you know, sort of, you can sort of think about it as upper bound on smoothness of this function. You can get high probability bound on the cumulative as well as simple regret. And the results are basically minimum of two bounds. One is the informational bound that is reminiscent of the prior works analysis, and another one which is a geometric bound. Now, what is interesting about this bound is that the regret is going to be a random variable with high probability. It actually grows according to a random variable. We call it the dimensionality near the optimal point. So it's a random variable as a function of f. If f has a small structure, d tilde will be small. If f does not have a nice structure, it potentially could be as large as d. So, so basically that's what I was saying. It gives you an opportunistic bound. If the function is nice, you're gonna have a better regret. If the function is not nice, then you're out of luck. You just have to accept the setting. And for all realization, this random variable is bounded by the ambient dimension d. So for Matern kernel, as I was telling you, this is going to give you a strict improvement. So between these two bounds, the informational bound and the geometric or dimensional bounds, this guy wins, and this is where you can see this result. So for Matern kernels with this parameter nu, and as I said, the useful ones is 1/3, 3/3, 1/2, 3 halves and 5 halves, you can see that with high probability, you will get that your bound in high probability is better for pretty much all dimensions larger than nu -1. This is dimensions greater than 2, you will get strictly better bounds. So we also get, we can also go back and do the analysis without the noise, and there you can redo the evaluations, and again you get better performance compared to a known algorithm in the literature, which is called Bayesian multiscale optimization. So this is the only algorithm in prior work that had this adaptive structure. So the idea is, it only works with the noiseless observation, hence why I specialized our theorem for this noiseless setting. And it works with a similar partition tree, but instead of using the variations that we had to account for the variation, it just works directly with the upper confidence interval. So you can sort of think about it, doesn't have that VH term that gives you the variational bound. So we can compare our algorithm directly with this algorithm. In terms of complexity, it's comparable to our algorithm. It grows only linearly with dimension, so you can actually apply it to similar problems. And in terms of regret analysis, it's very limited. That's not a problem of algorithm, you can apply the algorithm anywhere you want. It's a very powerful algorithm. But in terms of regret analysis, the regret analysis is very restrictive on which kernels they can give bounds, and it excludes the whole family of matterns, a whole subsets of family of matterns, such as half. For simple regrets, we can show that our bounds are strictly better than Bayesian multiscale optimization or BAMS2. So let me stop here and see if there's any question, and then if there's not, I'll just proceed with the second part of the talk. Okay, so now there's a lot of critique of the work I just described, in the sense that I have this unknown function, and instead of optimizing this unknown function, what I did is I put a prior, a Gaussian prior on this function, and then said, I know all the parameters of this Gaussian process, right? And I said, oh, if I don't know much, I make the variance wider. The typical trick of Bayesian work. And a lot of people complain that this is actually a very, very bad idea. You don't have a model for your function, but you assume you have a probabilistic model of where the function comes from. So what I'm going to talk about next is an agnostic setting where, again, remember, if the function, we don't have a prior on it, it's useless. Like the problem is ill-posed. There is nothing I could do except for exhaustive search. So I need some assumption. This, in the agnostic setting, the assumption is that F is in a reproducing kernel Hilbert space, and that is bounded in terms of its norm, and the observation noise is sub-Gaussian. So I have made the assumptions slightly less probabilistic, except for an upper bound. So what does it mean for F to sit in this reproducing kernel Hilbert space? Is that I am going to assume that my function can be represented by a linear sum of kernels, some kernel functions that are known to me, and this, this is not too complex in the sense that the norm is small, so I don't have too many CIs in this representation. Sort of this kernel methods is very reminiscent of how we think about, in signal processing or statistical learning of functions. So you basically imagine the function can be well represented by some samples if you knew where to sample and what is the kernel that gives you a good reconstruction, right? So so this setup says I don't have a probabilistic interpretation, but I have a prior knowledge that the function itself has some nice structure in terms of it can be represented as a linear sum of kernels. Now you would say, now you shoved all the complexity in knowing this kernel. The nice thing about this view is that you can take some samples, estimate a good kernel, and then use that estimate to go ahead with your algorithm. So you can imagine a data-driven version of the solution. And in fact, when I show you the empirical results, that's exactly what we do. We assume we don't know the kernel. We take some samples within a class of family of kernels, for example, let's say exponentials or whatnot. We estimate what is a good kernel to explain the data so far. So you take some sort of uniform, completely arbitrary samples, you make an estimate of the kernel, and then from that point on, you use this. So it's actually much more prone to realistic implementation for real functions. Okay. So now what is very nice is that even though this problem has no probabilistic structure, if you try to find the best function that satisfies, basically, so what you're going to end up doing is you have a bunch of xy's, and you're going to get the closest function in the space that approximates x and y. So you're actually doing a sort of an estimation of this function. Now, when you are trying to optimize and look for this function, your measure of error is quadratic or square error, then the posterior mean of a Gaussian process with zero mean and the same kernel K is the same as the solution to the ridge regression estimator of F. So now this is really telling me that even though this problem does not have a probabilistic structure, the two solutions are identical to each other. So I can just use the previous algorithms, any algorithm that I have for Bayesian optimization, to get a solution for this setup, this agnostic setup, where F is just lies in the space of linear sums of the kernels. Okay. Now, the implication is very simple, and this is known. This is not our work. In fact, there is a really nice paper that first exposed this Bayesian optimization, and in there they immediately saw this connection. So basically, if you come up with a solution for the Bayesian optimization, and in fact at the time, one of the most popular one is Gaussian process with with the upper confidence bound, UCB. You can just modify it and apply it to the setting by through this connection between the regression estimator and the posterior mean. And if you do that, you get a similar regret analysis, and you can show that the resulting regret bound is of the form square root of n. Now gamma of n is outside of square. You can use the same kind of analysis because of this connection between the two versions of the problem, and get a modified version of our algorithm. So you can take the same algorithm we had and now apply it in the setting that is the agnostic setting. So the modification goes as this. You take the same setup of these piecewise constant functions over these cells that are basically adaptively refined. You compute the UCB using the GP surrogate, right? So basically you can sort of think about that I have this GP surrogate that is equivalent. If I look at the posterior mean and the variance of it, it's going to give me the ridge regression solution. Now, instead of the variations that we're using the Gaussian process and the variability of a Gaussian process within a region to add to our function the variability. Now, I don't have the Gaussian process assumption, so I can't use that result, but I can just use the upper bounding from the geometry of these functions. In particular, since F can be represented as sum of my kernels, all I have to do is upper bound it loosely with the distance of these functions. So in other words, and these kernels, if if the kernel has any property like a holder continuity or whatnot, you get this for free. So here, when I write this, I'm assuming this is the typical kernels when they're smooth. Okay, so that's like immediately gives us an algorithm. And but then we are now using the smoothness of the kernel. The immediate question is, why not use the smoothness of F? So immediately we ask ourselves, can I make an assumption that not only F is actually can be represented in terms of the sum of the kernels that are smooth and with a bounded norm and such, can I actually make directly assumption on the smoothness of F? So, and if I do, what do I gain from doing that? So the simplest assumption is we said, what if F also lies in some Holder space? So that means that the kth derivatives are also Holder continuous with some exponents. If you do this, what you can do is, let me go to this figure. If you know that the function itself is smooth and its derivatives are smooth, now I can sample more than one point. I can sample sort of in a distributed location and use the samples to locally estimate this function with my favorite polynomial estimator, right? So the more points I have, the better fit of a polynomial estimator I can make. And if the smoother this function is, these estimates are better and better. So immediately, this will give us a variant of the algorithm where instead of working with an constant upper bound coming from this function, I can try to approximate the function in the cell because of the smoothness properties, and then build the upper bound based on that approximation. So instead of this loose upper bound that I had originally, we're going to improve on that upper bound by first approximating the function, then providing an upper bound on the function. The simplest is, if you don't have much smoothness properties, you just can take one sample and approximate it with a piecewise constant function, and then use that to build an upper bound using that variations. So these local polynomials now give us a lot of nice structure that can tighten this bound quite a bit. Is there a question? Okay. Is there a question? Okay, good. So the algorithm, so we defined, we refer to this modified algorithm.
I now see a question. Let me actually
okay.
ask.
Yeah, good.
Cameron Harris, did you have a question? Go ahead. You can unmute yourself.
Oh, I'll ask it, yeah. I'm just confused. Do we know the kernel in this setting?
Yes. The theoretical setting, you assume you know the kernel again. And when I will show you the empirical result, we will not. That's what I was bragging about it, that even though in the theoretical setting it's not that different from the Bayesian setting, the nice thing about the kernel methods is that you can estimate them for data.
Thanks.
Yeah. So with these local polynomial estimators, now you can get these tighter bounds and you can improve on the results. Again, I'm not going to give the full results, just there's a lot of equations, but instead try to give you a summary of what is the benefit of working with these local polynomials. Again, remember, I have the 3 partitions and then I have these local estimators. You can actually the interesting thing is, we first started looking at this problem by saying, okay, F is in the kernel space and it's smooth. It turns out for mature kernels, you can prove that the mature kernels, the functions do have smoothness properties, and you can actually compute what their holder parameters K and alpha are. So if you do that, then basically the second assumption is not really an assumption. It just follows from your original assumptions. Basically you can show that this LPGP-UCB algorithm achieves a tighter bound both on the simple regret and cumulative regret. The more interesting fact is that there is a lower bound on regret that can be obtained from an information theoretic argument. This is due to Jonathan Scarlett and his co-authors, where and there is a huge gap between all other prior work in terms of regret, both simple and cumulative, and this lower bound. And for us, for a range of mature kernels, and the range is when nu is less than d times d plus 1, you can say, like, if you put any reasonable dimension d, this is really nu less than 1. For these ranges mature kernels, the bound is tight. So basically our regret bound matches the lower bound up to a polylogarithmic term. So in fact closes this gap that was known in the literature. Another aspect that is useful is, beside these mature kernels that have practical use, practical interest by the users, we can actually also get for the first time, explicit regret bounds, explicit, I mean explicit in N, for other kernels, rational quadratic and gamma exponential kernels. By the way, our bounds for the square exponential, or Matern for new full half, the bounds matches the existing work in the literature, which is the GPUCB. Okay. Are there any questions on that before I sort of look at the sort of more, try to apply it and see? I am at 50 minutes, Mariam.
Yeah, five minutes.
Okay.
5 minutes left. Yeah.
Okay, thank you.
Thank you.
So, so I really like, by the way, this quote, because every time we take these theoretical ideas, that we learn quite a lot about how much we don't know how to scale them to practice. But I'm going to first show you the simplest example. This is, I call it empirical results, but empirical only in the following sense. So we have a synthetic function. We know the function. The function is basically a Brannan function. We combine them from various dimensions. So even though this is the ambient dimension is 8, it's defined on R8, we actually play with it and create a function that effectively only 2 variables are really, 2 dimensions are really important in your optimization. So this is where we expect to, for our algorithm, we would expect our algorithm to be good at finding the structure and basically zoom in on the maximizer faster than other algorithms. What I'm showing you here, so this is just the sanity check. Of course, the algorithm doesn't know F. We know F. We constructed it to see how the performance behaves. What I'm showing you in terms of performance, I'm comparing the performance of this algorithm with, just so that visually it's clear, with the expected improvement and probability of improvement algorithms, and a improved version of GPU-UCB, which is this purple line. GPU-UCB is known to be far more exploratory than expected improvement and probability improvement. So this is sort of not surprising that it does worse than those. Now the 2 top graphs are our algorithm. So the PS frag didn't work. I'm sorry, the name of these algorithms should have been more informative. So the red curve is the performance of the blue curve is the performance of our algorithm, the theoretical that I showed you. Its complexity is very high. When I was doing my local estimation of the polynomials, I ended up losing that benefit of growing linearly with the dimensions. Because if I want to fit a good polynomial in any dimensions, I need to sample as a function of that dimension. So I need my sample complexity to grow exponentially with the dimension. The red is our heuristic. It's a heuristic algorithm we came up, linearly grows with dimension. Computation is cheaper. In terms of performance, is not too far off from this algorithm. If anybody is interested, I can discuss what that heuristic looks like. This is just synthetic data. This is what, when we applied it to the first semi-practical algorithm. Here I am setting hyperparameters of a really simple neural network with 2 convolutional layers and 2 fully connected layers. And the hyperparameters that we're searching over are the batch size, learning rate, kernel size for each of the convolution layers, and hidden layers. So this is it. I believe it's a 5-dimensional optimization. To make the problem harder, this is the performance of the final neural net on a test set, which is a 10,000 sample of the MNIST data set. MNIST is well known to be too easy, so we're actually shrinking the training quite a bit to make the problem harder so that the performance of the algorithms are not all so good. And what you are seeing is the performance of our algorithm with the heuristic compared to the heuristic and so on. This is where we actually, so this is where we really try to take this algorithm and apply it to a real setting. This is the collaboration with Farinas Kouchamfar's group. We were looking at practical compression techniques that people do in accelerating a DNN on a specific hardware. And the compression parameters are pruning. You can throw away some of your connections in your neural network, some percentage of them, and the pruning parameter is that percentage. You can look at the quantization, with what bit precision your multipliers are gonna multiply numbers. You can do an SVD decomposition, the parameter of that decomposition. So these are the kind of practical tricks that people do to come up with these compressed neural nets. Of course, if you take any useful neural net out there like VGG16 or something, this is growing exponentially with the number of layers. So it's a really going to test your algorithm's performance. And in fact, the theoretical algorithms that we have had wouldn't work here. So what we did, we looked at the heuristic, and this is a joint work with Farinaz's group, is that we took this kernel method, but instead of working with these theoretically more complicated kernels that are nice to work with, we just took a simple Gaussian kernel. So now my kernels are Gaussian, and we are using the data to estimate the covariance functions of these Gaussians, but in a local fashion. So in that sense, it's similar to the local polynomials, but instead of approximated with a polynomial, we're approximating them with Gaussian kernels in those areas. And we did a batch sample version. So instead of sequentially pick every single sample, that was too expensive. We take 50 samples at any given time and run the sort of the test on those 50 hyperparameters or compression values. This is the performance. I'm just gonna show you, because one of the things that we learned is that the best competitor to us was a genetic algorithm that basically use the samples sort of using some tricks. And these are for sort of more practical networks that are of larger sizes and more useful for more complicated tasks. The nice thing about the framework we had looked at is that you can consider all compression tricks all in the same basket, which is something that the people in the acceleration community had not looked into. So in that sense, it performs better. And I am sorry, I'm a little bit over time, but almost on time to take further questions if there is any.
Thank you very much. We can use I guess there's a clapping.
Electronic.
Very nice talk. Thanks a lot.
Sure.
Okay, if there are any questions. Oh,
I think
okay.
Blake it said Blake.
That's right. So Blake, please go ahead.
Thank you. Welcome back. It's nice to have you visiting, Tara. Back, only a few slides back, like 26 or 25, your example, 2 active dimensions. Are these dimensions, do they have to be aligned with the original 8, or are you talking also about potentially a hyperplane of 2 dimensions?
So
a 2-dimensional plane that's tilted in the space.
Yeah, no, you're right. I have obsessing over that problem, that what if my dimensions are not lined up here? All of our algorithm, the notion of dimensionality around an optimal, which is what the algorithm does, if the dimensions have rotated, you will have to look at the rotation will fall in a higher dimension, but hopefully not as high as your ambient dimension. But you're right that potentially a really interesting question is, what if I actually have rotational, features? I feel like that's where this problem of the art of it is this assumption of writing it as a function of as a sum of kernels, right? So you can sort of do in practice, and that's what we did for this setup. What we did is, because exactly of what you were saying, what we try to do is to say, if you have dimensions that are related to each other, you would like to move along those dimensions, and the Gaussian kernel allows us to do. And I think there the art is using features that are elongated around some of the dimensions and maybe more compressed along others to create these linear dependencies. But the design of that feature space is all the art of it. Here we were labeling a Gaussian. I can generate all sorts of linear dependencies, and that saved us. But the
Great,
theoretical results is the real dimension.
Thank you.
Sure.
Okay, are there any other questions? I don't see.
I see some.
I don't see raised hands. Let me see in the chat window.
Yeah, I can't see.
I have.
Oh, Sriram.
Oh, yeah, Sriram. Go ahead.
Yeah.
It's a great talk. One question is, you mentioned that in the kernel setting, you can post facto estimate what are good kernels. I guess I have two questions. One is, can you deal with kernels of kind of varying widths, in your setting? Because,
that's a very good question. So the idea behind these local polynomials was to localize, and we are like, you can sort of think about it, maybe locally you will have some structure that is richer than other parts, and you can just sort of change that local parameter. We haven't played with it, but what you're saying is absolutely the right way to think about it, I think. And this is what actually Mariam was asking me, the connection to optimization. So if you take our algorithm, just say, let's say I would do a polynomial of degree 1. So I'm thinking about fitting planes to a locality. Now, when I decide to break my areas or expand my cells, what I inherit is the slope of this plane is going to give me the bounds in those regions. So there's some nice connection should be there in the gradient estimate, which was always bothering me, because in reality, when you do empirical even when you do first order optimization, in reality, you're going to take some samples around your point and estimate your gradient. So I was expecting our algorithm in some settings to do a mimic of estimating gradient, and this is that local polynomial is allowing me to do. Now, this is just like me. My student's a very precise person, and he keeps cringing. He couldn't come to this talk, but he would have cringed. What I've asked him to look at scenarios when we know the gradients are helpful, and see in those scenarios if our algorithm can beat the other algorithms by a greater margin because of this notion of gradient. And then the question is, where is the limit? Because you can take, now the polynomial can be a Newton, like when you go to quadratic, or like higher and higher, so you can do these estimates better. I think a good algorithm should try to figure out, oh, this is a good setting for me to do gradient estimates, and then just do higher order movements along the line. But this is just really me sort of conjecturing.
No, it's fascinating stuff. I have one follow-up question, if
Sure.
Yeah. So the thing is on the second part, where the kernel, you said you can estimate it from data, but also even in the Bayesian part, people do empirical Bayes, estimating it from data. So
Yeah.
What can give this a kind of conceptual barrier?
And I should say, I mean, I'm an information theorist. I have no problem with Bayesian view of the world, and it teaches me a lot. But if you want to be, but I've also seen people who like bash this estimating of the parameters of Bayesian as meta learning on the Bayesian's learning in Bayesian. So yes, I agree with you. You could do it, and there are practitioners who do it very successful. Philosophically, is it defendable? I don't know. As a person who is often a Bayesian a Bayesianist, I am sympathetic to what you're saying, but it's a big no-no in some philosophical terms.
Got it.
I don't know if you know the quote that I put up, the epistemic ignorance cannot be approximated by a probability distribution. It's actually, these papers are really fun to read if you have any time. This John Norton and others.
Sounds like a great pointer.
Philosophical. Okay, we have a few thank you messages posted on chat. Mehran is thanking you, Krishna, and there's one quote saying that the talk was very captivating. So with that, let's end the colloquium and let's thank Tara again. Thank you very much.
Thank you.